Yeah.
Thank you.
Christian is going to take over.
All right, yeah. Hello everyone, I'm Christian. This is my title, What Nature Refuses to Tell Us. Sounds a bit mysterious, but I'm going to explain this in the following, what I mean by that. So what I'm going to do during the next 40 minutes is the following. So actually, some time ago, we sent you guys a survey, which some of you filled out, where we asked you a couple of questions, and one of these questions was, what's for you the most interesting scientific fact? And you guys gave very interesting and fun answers, stuff like babies don't have kneecaps. Not sure if it's actually true. I mean, we cannot discuss. But also, you know, other interesting things, stuff related to the fine-tuning of the constants of nature in our universe, which is very interesting, or also things related to entropy. You know, if you of combinations this deck of cards can end up with is basically exceeds the number of atoms in the visible universe, right? So I read this and I saw that the scientific fact that I myself find most interesting is not on this list. So I thought I will make my life very easy and I just tell you what my favorite scientific fact is. This is what this talk is about. One thing, somebody wrote this down. This is something that I liked specifically. When traveling at incredibly fast speed, time dilation makes both sides observe the other going slower. The reason why I like this so much is because this is actually a scientific fact that is at the very basis of one of the most important theories that we have in physics, the theory of relativity. And this is also true about my favorite scientific fact. My favorite scientific fact is actually at the foundation of quantum mechanics. So what all these things have in common, they are somehow a little bit crazy, right? A little bit unexpected. But this thing here is not so crazy that we cannot make movies about it. So, you know, if you don't know this movie scene, you know this is from the movie Interstellar. Matthew McConaughey crying his eyes out because he spent, you know, 2 hours in a spaceship close to a black hole. And during these 2 hours, his daughter aged by 27 years. So even though this is a crazy scientific fact, we can still somehow imagine it, right? We can sort of imagine what it means. This is not true about the foundation of quantum mechanics, as you will see. There we have no way of really sort of, with our human brains, sort of really imagine what it means because our experience is so far away. Actually, a lucky coincidence is that my favorite scientific fact is also the one which we celebrate this year. It was discovered by Werner Heisenberg in exactly 100 years ago, in May 1925. And what Heisenberg discovered in May 1925, if I would have to put it in one sentence, I would say that he discovered that nature doesn't reveal everything to us what we would like to know from her. So there is a fundamental, some people phrase this in a way that there is an uncertainty principle in nature. And maybe some of you guys have seen that. This is the famous Heisenberg uncertainty principle, which says that if you want to know the position and the velocity of a quantum particle, you cannot measure these things simultaneously. So if you want to measure the position of a particle to some accuracy delta x and the momentum or velocity to an accuracy delta b, the product of these things is always larger or equal than some constant. This is how people phrased this. And when I learned the first time about this thing, this was sort of my reaction. I didn't get the point. You know, what is it about? Like, what's so interesting about this thing? Actually, Heisenberg's thought was much deeper than that. And I realized that when I read his book, his autobiography, some years later. And what Heisenberg really said is that on the quantum level, you know, if the objects get really small, there is a fundamental indeterminacy of their properties. So properties of objects don't need to exist. So in other words, the electron in an atom, it does not have a position. It really has no position. And it's the act of measurement, actually, when we measure it, then sort of the electron becomes a position, or like the electron gets a position from the process of the measurement. But before we measure it, the position is uncertain. It's not that we don't know the position, the electron really has no position. And it has no velocity. These properties don't exist. And this is something that is outside of our, we cannot imagine this. There is no way of making a movie about this. And this is sort of the reason why this is my personal favorite scientific fact. So it was this insight that Heisenberg had 100 years ago, that these properties are fundamentally indeterminate, which sort of kicked off this our understanding of nature as we have it today about matter. So his point was that you cannot describe atoms by attributing properties to them that they don't actually possess. And this development had an enormous amount. This is the second reason why I like this scientific fact so much. It kicked off at an enormous amount of scientific breakthroughs and also technological breakthroughs. So when we understood this, actually we could use this to understand the light which is emitted by atoms, the experiment that you have seen in the morning. We also then later understood, how light, what's the actually complete quantum theory of light and how it interacts with atoms. Nowadays we call this quantum electrodynamics. It also helped us to understand the nucleus of the atom. We call this theory quantum chromodynamics. And this theory also helped us to understand, complicated phase of matter like the superconductors that you have seen just a couple of minutes ago. Okay. And it also, many technologies that we use today are based on Heisenberg's discovery 100 years ago. Things like NMR lasers, solar cells, the transistors that are in our smartphones, all these things are based on this discovery. Okay, so let's see.
Restart.
Starting. By the way, if anything is unclear, just ask. Just interrupt me anytime. All right. So this is actually what we celebrate this year. It was Heisenberg's discovery which made all these technologies actually possible. Without understanding quantum mechanics, you cannot understand these technologies. And actually, sort of in the mid-80s, another development started, which we now call the second quantum revolution. Also, Hossein mentioned this. Where it turned out that this discovery from Heisenberg that properties don't exist before we measure them made us think differently about information. So before this, we thought about information like if we want to learn something about the system and we measure it, actually what we do is we uncover what it actually is underneath. But in quantum mechanics, quantum mechanical systems, they don't have their properties defined before the measurement. So it's not about asking what are the things actually underneath. It's more about asking how do quantum systems respond when we measure them. Or how do quantum systems respond if we ask questions to them. And so this gave us a different perspective on information, which we call quantum information. And one of the basic concept in this quantum information realm is the concept of quantum entanglement. And my talk, what I intend to do is basically to explain to you what these two things are, what this means. So another thing, maybe another thing to mention, there was something very important happened in 1994 here in this context, by a discovery by Peter Shor, who is a professor at MIT here. So he discovered that this sort of insight from Heisenberg also makes us think differently about the complexity of problems. So he sort of figured out that if we have a machine that can process quantum information instead of classical information, we can solve problems much more efficiently. So there are problems where we previously thought they have no efficient solution, but if we have a quantum computer, then we can efficiently solve these problems. And after my talk, Tommaso will tell you a little bit more about quantum computing and which kind of complicated problems we sort of try to address with them. All right, so let's dive in to quantum information and quantum entanglement. So what is actually information? It's pretty hard to define, but actually one of the most important insights of information theory in the 20th century was the insight that information consists of smallest units, which we call bits. So a bit is something that can take two values, on or off, or usually we call them 0 or 1. And you really need these two things to encode information. Imagine we would just have zeros, and I would like to write an email to one of you guys. You get an email which is just full with zeros, you cannot read it, right? But if we have something that can take two values, 0 or 1, we can define a language. We can say 0, 0, 1, 1 is an A, 0, 1, 0, 1 is a B, and you get an email with zeros and ones, and you can actually read it. So as soon as you have something that can take two values, then you can transmit information. So this is the concept about bits, and if you ask what are these bits in our devices nowadays, they look something like this. So this is an image of a small transistor that stores a charge on a small sheet of metal. It's about 50 nanometers in size, and our devices, like our smartphones, they have hundreds of millions of these little devices, and this is how we store the information. This is how classical information is stored. Quantum information, what we have are different objects. Actually, here at Harvard, we are using single atoms to store information. So actually, a bit is not stored in a device like this, but actually just in a single individual atom. We nowadays have the technology that we can trap and manipulate individual atoms. And sometimes it is instructive to think about these bits in the following way. You can think about them as boxes where you can store a ball, okay? So let's say the bit value, if it's 0 or 1, is represented by a ball, either a blue or a red one. And what you can do with classical bits is you can open them, you can put the ball into the box, and you can close them. And after a while, when you are interested in the bit value, you can open the box again and look what's inside. That's sort of how classical bits behave. And this is really everything you can do with classical bits. You can write them and you can read them. That's the end of the story. Quantum bits behave fundamentally in a fundamental different way. And there are different ways of talking about quantum bits. So in this survey that we sent out to you guys, somebody already wrote down that a quantum bit is something that can be 0 and 1 simultaneously. But actually, there is a better way of thinking about quantum bits. And this way was introduced by the physicist John Preskill. He is a professor at Caltech. And I will heavily draw basically from his lectures and insights in the following minutes. And what he sort of said, these quantum bits, you can think about them as boxes that have 3 doors. So a door number 1, a door number 2, and a door number 3. And imagine you want to assign the bit value 1, so the red ball, to these boxes. You can do that in 3 different ways. So you can open door number 1, 2, or 3. And you can put the ball inside the box and close it. And actually, if you open the same doors that you use to put the ball into the box, the same ball comes out again. So in this way, quantum bits are behaving exactly the same way as classical bits. But if you put the information into the box through these 3 doors, so door number 1, 2, and 3, and then open different doors, what happens is you get a random outcome. Completely unpredictable, completely random. 50% blue, 50% red. So I would just like to show you this one more time because it's so important. So putting these balls into these boxes and opening the same door that you use to put the information in, you see the ball. But if you put the balls into the box and now open different doors, the outcome is completely random. So this maybe doesn't strike you as particularly interesting. Yeah. Yes.
For quantum information, are there in this scenario, like the red and blue, that still be stored as zeros and ones?
Yeah.
Or it'd still be zeros and ones, but
I just replaced the zeros and ones with red and blue.
okay.
Okay, just to give
When
you
you
a
open
sort
different
of.
doors, you can't determine which value you'll get if it's not the same door that you put in.
Say it again.
I guess you're saying the difference is that when you like put into the box, for example, you can't determine what value you'll get when you open it if it's not the same door that you put in.
Yeah, exactly. Exactly. This is what it is. So why is this interesting? It's interesting because this actually means that it's hard to copy a qubit. Like if I give you a qubit and I ask you, please make a copy for me, what you have to do is you have to open it to see what's inside. And if you open the door that I use to put the ball into the box, then you can see the bit and you can copy it, no problem. But if you open accidentally a different door, you destroy the information because you get a random outcome. It's completely random, 50% blue, 50% red. So in a way, these qubits are copy safe. You know, you need this additional information of how they have been prepared in order to copy it. While these classical qubits, you can just copy them, right? You just open it and look what's inside and it's done. Yeah.
What are like the doors like analogies for? Like
yeah, very good, very good. This is a little bit abstract, okay? So to make it a little bit clearer, I'm not going to talk about this in detail, but maybe Tommaso can say 1 or 2 words about it. So these bits are actually atoms, you know, and nowadays we can trap these atoms. We can trap them in electromagnetic fields. We can trap them in tightly focused laser beams. We now really have the technology to trap single atoms. And we can shoot laser beams on these atoms. We can manipulate them with laser lights and sort of manipulate in which state the electron sits. And this whole business, what I just told you, of opening the box, putting a ball inside, opening another door, we can translate all of that into laser pulses on atoms. Okay, so for instance, in the context of ions, for example, this is something I worked with quite a bit. You shine a red laser pulse on the atom followed by a blue laser pulse, and then you make a picture of the atom with a camera. And this actually would correspond in this picture to opening door number 2, putting a ball inside, and opening door number 1. Okay, we can just translate all these things into laser pulses on atoms without giving you much more detail about it. Okay. But these boxes are sort of the abstract way of thinking about them. But single qubits are actually not very interesting, besides that they are sort of copy safe. But the situation changes fundamentally if you have more than 1 qubit, if you have 2 qubits. If you have 2 qubits, you can do the following. We can actually shine a laser of these 2 atoms that puts them into a special, and now I'm saying the word for the first time, into a special quantum state, such that the following thing happens. So I prepare now 2 of these qubits, 2 of these boxes, and I will do it over and over again, okay, repeatingly. And let's for the moment just look at one of the boxes, at the left one. Okay, so I will repeatedly prepare these boxes, and we just look at the left one and opening the doors. And what happens here in this specific case, no matter what you do, if you open door number 1, 2, or 3, the outcome is always random. Always 50% blue, 50% red. No matter what you do, if you open door number 1 or door number 2, there is nothing you can learn about it. It's always completely random. Let's do the same thing, but only look, now let's ignore the left qubit and only look at the right qubit. We open 3 times door number 1, sometimes blue, sometimes red. We open 3 times door number 2, sometimes red, sometimes blue. We open 3 times door number 3, sometimes red, sometimes blue. It's completely random. What this means is that these qubits, they contain no information, right? So you cannot learn anything about them no matter what you do. But that's a little bit strange because on the slide before I told you that you can store a bit of information, right? You can put this ball into the box. So the question is a little bit where is the information hiding in this case? And it turns out that in this example, all the information is hidden in correlations. And what I mean by this word correlations is if you open the same door on both boxes, you see the same ball. So if you open, it's always random, but if you open the same door on both of them, the same ball comes out. And this is something that quantum information can do that it's not possible with classical bits. So this concept that the information is not stored in the qubits, so with classical bits, the information is stored in the bits, right? So a bit can be either 0 or 1. But here the individual bits contain no information, but all the information is stored in correlations. In order to read the information, you have to open at these 2 qubits simultaneously. This phenomenon, this is what we call quantum entanglement, and this is really at the basis of quantum information theory. So maybe this is a bit abstract for you, but let me try to make it a little bit clearer why this is fascinating and why this means. So we can prepare 2 of these entangled boxes and send these boxes to 2 people. Usually we call them Alice and Bob. And so Alice and Bob can now open these doors. So they open actually Bob can be pretty far away. That's actually one of the fascinating parts, you know. Bob can sit in Andromeda galaxy. We send 2 qubits to them. And they both, let's say they both open door number 1, they see the same ball. Yeah. They can call each other on the phone. Alice, what did you see? I saw a red ball. Yeah, me too. They can do this again. We send them other 2 boxes. They open door number 3. They see the same color. We send them again 2 boxes. They open door number 2. The same color. They do this a gazillion times. So they always see the same thing if they open the same door. Yeah?
Wait, do they have to open the door at the same time?
They can. Yeah.
Okay. But if they do it at different times, they'd still see the same.
In principle, if they do it different times, they see the same. But actually, the fascinating part is that they can do it at the same time.
Okay.
So they would see the same color, even if Bob sits in Andromeda galaxy. If they would open the box simultaneously, they would see the same thing.
So like, but if Bob opened the one in Andromeda galaxy like 30 years before Alice did, like with him opening it, it determines what's in Alice's box, even though she hasn't opened it yet.
Like if the time difference between this is so large, you could actually imagine that one box sends a signal to the other one, right?
Okay. Yeah.
But if you open them simultaneously, you kind of ensure that this is not going to happen.
Yeah, so it's like still a signal traveling, but just
Right. Yeah. But there is a different thing to this, because this stuff that I explained to you now is not particularly interesting, right? Or at least, let's say, Bob, after doing this for a while, Bob figures out, actually, this is not so interesting. Because what Bob thinks what happens here is these boxes look like this. So the balls are already waiting behind the doors, right? And if he opens, let's say, door number 1 on his box, the red ball comes out, and the other 2 balls for some reason disappear, right? And the same thing happens on Alice's box. If she opens door number 1, the red ball comes out. So what Bob thinks what happens here, and this is a perfectly valid explanation in this scenario, is that boxes are just identical, right? That's all what it is about. So if you would open door number 3, blue ball comes out, and same for Alice, and the other 2 balls are gone. We never have a chance of looking at them. So what's actually so special about it? Actually, the special thing, you can see it if you start to open different doors on these boxes. So let's say Alice proposes this. So Alice says, Bob, we opened now the same door for 20 years, you know. A gazillion times we have verified that we saw the same ball. Why should we not start open different doors? And Bob says, okay, this is a good idea, but before we do that, let's maybe think a little bit about it, what we expect when we open different doors. So that's the situation that Bob has in mind, right? They have two identical boxes with the balls waiting behind the doors. So when they start opening different doors on the boxes, how many options do they have? Does anyone know? Does anyone want to tell me? Like how many options are there for opening different doors on the boxes? 6 is a good number. Actually, there are just 3.
Oh, I meant like ordered.
Ordered. There are 6 ordered, but the boxes are identical, right?
Yeah.
So they verified this a gazillion times that these boxes are the same. So actually, these are the 3 options they have, right, to open different doors on the boxes. The next thing you can ask, how many different boxes are actually possible? And the answer is 8, right? So these are all combinations of balls that you could imagine. You have 3 doors and 2 colors, so you have 2 to the 3 options. These are these 8 options. These are the 8 type of boxes that we could possibly send to them.
So,
Yeah.
So that means that we're treating opening, that Alice opens 1 and Bob opens 2 is the same as Alice opening 2 and Bob opening 1.
Yeah.
Okay.
Yeah.
I just want to make sure I understand that.
This
It doesn't matter who
it
opens which
doesn't matter who opens which one,
Okay.
because the boxes are identical,
Okay.
right?
Yep.
Exactly. So these are these 8 options for different boxes. And if you look at them, you maybe realize something. In all of these 8 options, there are always 2 balls which are the same, right? So we have 3 doors, like 3 balls, but only 2 colors, right? There is no way that all 3 balls can be different, right? At least 2 must be the same. There is no way. And this means if you have 2 boxes like these ones, one of these 3 options here must give you balls of the same color. Do you see that? Does everyone see that? There is no way around. So if Alice and Bob receive these boxes and open different doors randomly, in at least 1/3 of the cases they have to see the same color. There is no way around, you know, because if you have 3 balls, 2 must be the same, right?
Sorry,
Yeah.
is it independently of the state or is
If it's like Bob imagines it, you know, like if these are boxes of this type, like two classical boxes with balls waiting behind the doors, like one of these 3 options must give you balls of the same color, because this is everything that exists. So this is our conclusion, you know, if they receive 2 of these boxes and open different doors and get again 2 boxes and open different doors randomly, in at least 1/3 of the cases they have to see the same color. There's no other way around. Now they do the experiment, this actually has been done. They open different doors, you know, they get boxes and boxes and open different doors. And what they find is that they see the same color only in 1/4 of the cases. This is what quantum entanglement is. So they of course wondering what's going on. Actually what we learned from this Heisenberg was right. This picture is wrong. It is not that these boxes are waiting behind the doors. Yeah? It's the moment you open the box, the color sort of comes into existence. Before you open the box, the color of the balls didn't exist. This is the proof. Okay? To make this a little bit more vivid, you can now ask, is this useful for anything? Let's say, like, can we make money with it, right? Say we have, you know, there is a quantum casino which offers a game of the following type. So one of you guys with your friend are going to a casino. The game is the following. You get 2 boxes from a croupier, and the croupier guarantees to you that these boxes are the same. They are absolutely the same. So You can always open the same door and see the same ball. They are equivalent. And the game is now the following. You have to open a different door than your friend. So you have to open different doors. And if you see the same color, you win. And the croupier pays $8. And if you open different doors and you see different colors, you lose and you have to pay $3 in that case. So is it a good idea to play this game? So if this game is offered in any casino you will ever go to, you should immediately buy in for as much money as you can. Because if these boxes are classical, which will be the case in any casino on this planet at the moment, we have no quantum casino yet, then in 1 out of 3 times you will see the same color. So 3 times you win, like you have to sort of pay $6 here and you win $8 here, so you are on average winning $2 per 3 games. But if this is a quantum casino, you will see the same color only in a quarter of the cases and you will lose $1 per 4 games. So the casino will have what we nowadays call a quantum advantage by having access to quantum intelligence.
Why exactly is it a quarter? I don't quite...
Well, this is a deep question, and I can go through you with that, but to derive you why it's exactly a quarter, it's only a quarter in a specific case that I constructed here. I'm happy to discuss that with you, but I cannot explain it here. It's a special construction where it will be a quarter. Right, so this is a stupid casino. Like if I'm now, founding such a casino, I will not be able to make any money with it if some of you guys visit, because you understand now quantum and you will not play it, right? So, like for my final part, I actually wanted to discuss something that's more useful. And before I do that, how much time do I have left?
Oh, you started roughly at the time.
Still have 10 minutes or so? Or maybe?
Yeah, you have a,
Okay.
yeah, you have a good time.
Okay. So let me tell you a real world application, okay, for this. The most interesting application is quantum computing, which I'm not going to talk about. Tommaso will do that a bit later. But also in this survey, when we asked you what's interested, actually I counted 6 people sort of put down cryptography. So I will talk about cryptography. Not sure yet. Okay, one final thing. These experiments have not been done by Alice, Bob, and the croupier, but by these 3 gentlemen here. They really did exactly that, and they got the Nobel Prize for doing it in 2022. They did it not with boxes, but they did it with particles of light, with photons. But this proved that Heisenberg was right, that these properties don't exist before we measure them, and this was worth the Nobel Prize. It's a very deep, also deep philosophical insight, into nature. Cryptography. So what is a real-world application of this? Cryptography, the task of cryptography is to transfer secret messages. So let's say Francisco wants to send a secret, he wants to gossip something with Oriana, happens quite a bit here. So he wants to send a secret message. So, sending secret messages, sometimes what you do is you password protect the file, right, somehow. So an intuitive picture for this is like Francisco can buy a box with a key. He can unlock the box, put his secret message into the box and lock the box up again. And then he can send it to Oriana. But Oriana is then asking, okay, what's next? What should I do now, right? I cannot open this box. So the dumbest thing Francisco could possibly do is sending the key to Oriana, right? So you should not send passwords via email. But what he could do is he could maybe give the key to somebody he trusts, right? To a trustable person, and this guy brings the key to Oriana. But if we trust this person, it's not so clear, right? Like it's not the best strategy. Actually, this is not how modern encryption systems work. We are using like asymmetric encryption system, and this is actually pretty clever. It works like this. If Francisco wants to send a secret message to Oriana, Oriana has a padlock and the key to the padlock. What she does is she unlocks the padlock and sends the open padlock to Francisco. So Francisco can now, go to Target and buy a box, put the message into the box and just clip it, lock it with Oriana's padlock and now send the thing to Oriana. And Oriana can now unlock it because this key here, she kept it secret all the time, right? That's the idea of modern encryption. This is, it's called asymmetric encryption. In this case, this padlock here would be called the public key. Everyone can sort of see it. And this here would be the private key that Oriana keeps secret to herself. And these systems are sort of based on a concept that we call trapdoor functions. These are functions that are very easily computable. So you can compute f of x pretty easily. But these functions are extremely hard to invert. They can only be inverted if you have additional information, which is called the trapdoor. And the question is, how safe are these things? Like, is it possible by seeing the public key, could you actually figure out what the private key is? And our idea is this is very, very hard to do. Ironically, what Peter Shor discovered, if we would have large-scale quantum computers, they could actually do it, Quantum computers could compute the private key from the public key. So there are some ways of attacking these systems. But quantum cryptography actually provides a way such that Francisco and Oriana can share a key and nobody else, even in principle, sort of can figure out what their private key is. And this works in the following way. So let's say this is my little quantum computer, and what this quantum computer does now, it creates entangled qubits and sends them to, like the same that we had before with Alice and Bob. Entangled qubits are sent to Francisco and Oriana. So it just keeps, generating entangled boxes and sends them to these guys. Quite a couple of them. And when they have them, what Francisco and Oriana do now is they open these boxes completely randomly. Okay, so Francisco opens his boxes through whichever doors he likes, and Oriana is doing the same on her boxes. So they're just opening all of them. And then once they have done that, they publicly announce which doors they opened, but which colors they have seen, this they keep secret to themselves. Okay, so which doors they opened, everyone can see, but not the colors. And now, if these people, if Francisco and Oriana open these doors randomly, like since there are 3 doors, in average, in a third of the cases, they will open the same door. So in this case, in these cases here, you see they open the same door, and they know that if they open the same door, they saw the same color, right? This is what they know. This is the feature of entangled qubits. So every time they open the same door, like here, here Francisco opened door number 2 and Oriana opened door number 2, and they saw a red ball here. And in this way, actually, here they opened the same door 9 times. So now they know that they have the same, they generated a secret password, which only they can know. And you can show, actually, people showed that this is sort of secure against all types of attacks. So something one could imagine is when a box gets sent to Oriana and Francisco, there is a little devil, like a little eavesdropper that tries to figure out what is going on. So what Ruben could do is he could look at the box, he could open the box, look what's inside. Aha, a blue ball is inside. He puts it back into the box. But if you remember my first slide, what I told you, if you put a ball into the box and you open now another door, the outcome is completely random and unpredictable. So in this case, Oriana and Francisco will notice that sometimes when they open the same door, they don't have the same color. So then they have to be careful. You know, somebody might have interfered with our qubits. So they can actually see if an eavesdropper is in the channel via this entanglement. Another thing one could imagine is that the eavesdropper sort of hijacks this quantum computer that sends the qubits and actually prepares boxes, you know. Yes?
So even if, like, so you're saying a message could be understood by the receiver, even if, like, all of the, like, I guess I don't get, like, if not all of the, you know, they don't all open the same box, which only, you said only a third of the time.
Yeah.
How can they receive the message if
So they open random boxes, and in a third of the cases, they will open the same box and then see the same color.
Okay.
And in this way, you know, like, depending on which colors they have seen when they open the same box, red or blue, they have now a bit string here.
Yeah.
And this bit string is a password. And not only Francisco knows the password, but Oriana knows it as well because she saw the symbol.
Okay.
And this they can now use, this password, Francisco can now use to protect some message, send it to Oriana, and Oriana can actually read it because she has the same password. That's sort of the idea. So if Ruben hijacks this quantum computer and prepares boxes where the colors are already waiting behind the doors, actually this is also not very helpful because, you know, 2/3 of the, like 2/3 of the time, Oriana and Francisco will open different boxes, different doors. And you know from before that when they open different doors, there is this strange phenomenon that they see the same color only in a quarter of the cases. And actually Ruben cannot produce this situation by, you know, putting balls behind the doors, because in such a situation, when he knows what's going on, when they open different doors, they will see the same color only in a third of the cases. And this, again, in this way, they can check if somebody hijacked this quantum computer and actually knows which boxes are sent to them. And there are also other type of attacks where you can check that this is secure. And this is a way of secure communication that is protected by nature and not by some principle like a trapdoor function. So with this, I'm actually at the end of my talk, and my final statement is, you know, we had this amazing development since Heisenberg discovery. We are now in this new era of the second quantum revolution, where quantum information and quantum entanglement play such a huge role. And this field is actually currently kind of starting. You know, we don't have quantum computers yet. We have sort of prototypes which can do these things. And I just make the final statement. Some new ideas are here needed. Yeah. So anyone who is interested in quantum physics, so this is a field where a lot of discoveries are still possible. And this is the end of my talk. So thank you for listening.
Let me make a note that one of the advantages of this protocol is that if Ruben manages to break the cryptographic scheme, I'm also happy because it means that we learn new physics. So I don't mind that he figured out with us.
You might get a Nobel Prize for that.
As long as he shares it, I'm okay.
And by the way, it's